So today I'm going to try and explain the intuition and ideas behind a basic hypothesis test, and we will see this logic that will develop now in a variety of settings. So this we can think of as the template or the framework for thinking about doing hypothesis tests. So I'll slowly walk through the slides, and you can do it more leisurely and also be reading the textbook in chapters 2 and 3 where they Stock and Watson talk about hypothesis tests. So it's very important for you to try and understand this now and spend some time understanding it. It's the hardest conceptual part of the course, so it's well worth spending several hours trying to understand this now. And of course, you spent many hours learning this in Math 8 and Almost 40, so it should be familiar to you. If you didn't understand it then, now maybe it's sunk in a little deeper, and seeing it again will help you understand it. If you still don't understand it, if you're still not convinced of the intuition, we're going to be talking about it all quarter long, so do come and see me in office hours to go over more problems or raise it in class, and I'll be happy to go through this again. Okay, so we'll start. We'll start by saying, suppose we have a variable, and let's call the variable age of students. So we'll just call that X. And we have a hypothesis about the age of students, that the average age of students at Santa Clara is 19.75. So we're going to sometimes call that our null hypothesis. That's our starting point. That's what we think is true about the population of students at Santa Clara University. We think that the average age is 19.75. That's our null hypothesis. We know that there's some older students. We know that there's some younger students. And we're interested in determining whether our hypothesis, our null hypothesis that the average age is 19.75, is likely to be right, or maybe it's not right. So we decide to take a random sample of students to see if we're right. And we want to emphasize the randomness of the sample. We obviously don't want to take a non-random sample. We don't want to take a sample of seniors and ask them their ages, because they're not representative of the population of students at Santa Clara University, and they'd obviously be older than the average or typical student. So we take a random sample from all the students, at Santa Clara University, and then we'll use that random sample to conduct a hypothesis test, to test our hypothesis that the average age is 19.75. So we take a sample, let's say, of 200 students, and we find that the mean for those 200 students is 20.15. So the mean is not 19.75. It's a little higher. And we also find, we're going to use this in a minute, we find that the standard deviation of the sample is just 1. So make it real easy to do calculations. We'll just say the standard deviation is 1. Remember, standard deviation is a measure of spread. The standard deviation is the square root of the variance. If the standard deviation is 1, then the variance is also equal to 1. So that's the variance of our sample of 200 students that we got. So the question is, should we continue to think that the average age of 19.75 is right? Because after all, what we've got here is just a sample, and where we found in our sample it's 20.15, so maybe we shouldn't change our hypothesis that the average age is 19.75, or maybe the sample of 200 students should lead us to revise our hypothesis or reject our null hypothesis, and maybe formulate a new hypothesis. And presumably our new hypothesis would be that, maybe the average student at Santa Clara is actually a little older than 19.75. So that's our question. That's our hypothesis test. Now, 20.15 is, of course, as I mentioned, different from 19.75, and the difference is 0.4. And what we don't know is whether this difference is big or not. Is it big enough that we should change our null hypothesis, revise our prior idea about the average age of Santa Clara University students, or is 0.40 small? And if it's small, then we shouldn't revise our hypothesis. So we have to have a way of determining or assessing whether this difference in the mean from our hypothesis, this difference between 20.15, the sample mean, and our hypothesis, 19.75, is that difference big? Now, in thinking about whether it's big or not, it's important to notice or remark that a different sample would have generated a different x bar, a different sample mean. So we can think about x bar as a random variable. It's a random variable because if we'd drawn a different sample, it would have taken on a different value. And every time we take a different sample, we'll get a different value for the sample mean, for x bar. So this x bar, this sample mean, will have a sampling distribution. Sometimes it'll be high, sometimes it'll be low, it'll be different every time. And that range of variables, some more likely, others less likely. It's very unlikely that we'd take a sample of students at Santa Clara University and find that the average age was 7 years old. It's possible that we have some brilliant 7-year-olds that I'm not aware of, so that's very unlikely, right? But it's possible we could take a sample of students at Santa Clara University and there's a 50-year-old in the sample, and so the average age ends up being 35 years old. In that small, maybe, sample. So we want to know what the sampling distribution looks like for the sample mean. We could just take a whole bunch of samples, like take 1,000 samples of 200 people each. That'd be very expensive, very time consuming. And then we'd know what the distribution of this sample mean would look like, because we'd have 1,000 different samples, 1,000 different sample means, and we'd get some distribution. Distribution, remember, looks like this often. This is the bell-shaped curve for distribution. We talk about these as the tails of the